My name's Kevin, and I'll be talking about a recent project, Logsmooth gradient concentration and tighter runtimes for Metropolized Hamiltonian Monte Carlo. This is joint work with two awesome collaborators from the University of Washington, Ruoqi Shen and Yintet Li. So let's get started. So this paper studies log-concave sampling, which is the algorithmic task of sampling from the density proportional to x of minus f of x, where the function f is convex. So let's see some examples. When f is quadratic, this is asking you to sample from a multivariate Gaussian. And when f is the indicator of a convex set, this is asking you to uniformly sample a point from a convex body. So this restricted problem of convex body sampling was studied by Dyer, Fries, and Canaan in the 90s, and they gave a polynomial time algorithm for this. And since then, a variety of recent works have brought the more general problem of log-concave sampling all the way down to d to the 4 in runtime, in terms of number of oracle queries of f. And in this sense, log-concave sampling can be thought of as a basic tractable sampling problem, in the sense that it's a wide family of common distributions, which emit polynomial time samplers. So here are a few examples of this uniform sampling problem. Great. So it turns out that in this basic tractable case, the problems of sampling and optimization are intimately related. So one way to see this is that it's well known that a log-concave sampler would instantly imply a convex optimization algorithm as well. And I should point out that in the non-convex cases, these are very different, as has been noted by several recent works. So let's survey a little bit the complexity of these problems and what's known. So for convex optimization, there are two very popular regimes. And the first one is simply the general regime, where f is just assumed to be convex and no other assumptions are made. So here it's known that you can find an epsilon approximate minimizer in roughly d squared log 1 over epsilon function queries. And here the oracle model is, I give you a point x, and the oracle tells me the value of the function at that point. And this is natural because, this is known as the 0th order oracle. And this is natural because f may not even have higher derivatives if it's just convex. Now in the well-conditioned case, where f has more structure, namely it's sandwiched between two quadratics, an upper bound and a lower bound, and this is a notion I'll make more formal later. We can study this through the lens of a first-order oracle, where given a point x, I also query the gradient of f at that point. And this is simply because the upper bound quadratic implies that the gradient of f is Lipschitz and well-behaved. Now in this setting, given a condition number of kappa, which is the ratio between the upper and lower bound leading coefficients, Nesterov's accelerated gradient descent algorithm obtains an epsilon approximate minimizer in roughly square root kappa log 1 over epsilon queries to a gradient oracle. And this setting is particularly nice because in a variety of generalizations of this problem, matching lower bounds are known to these algorithmic upper bounds. And you can also assume higher order derivative bounds on the function, but this talk will focus on this most basic case, where all you assume is this sandwiching of the second derivative. Cool. So now let's talk about the complexity of log-concave sampling. And I'll remind you that this is a task of sampling from x of minus f of x, where f is convex. And in this setting, there are also general and well-conditioned regimes, which correspond to the corresponding assumptions on the negative log density f. And admittedly, correspondingly, these regimes are studied through the natural lenses of 0th and first order oracles. Now, a natural question to ask is how precisely do we know the complexity of these tasks? And it turns out the answer is not very well at all. And we'll see what I mean by this. So on the lower bound side, very little is known, and specifically most lower bounds that are known are algorithm specific. If you have more thoughts on this, I'm happy to chat further. And furthermore, on the upper bound side, it's widely believed that most of the upper bounds we do know are not tight, and that the tightness of these upper bounds are linked to fundamental geometric questions about log-concave distributions. So for instance, the famous Canaan-Lovász-Simonovitz conjecture asks, what is the worst isoperimetry of any log-concave isotropic density? And here isotropic just means it's been normalized to have the covariance of the identity. And the conjecture says that this is a dimension-independent constant. And if you were able to resolve this conjecture, you would instantly have faster sampling algorithms in the general log-concave setting. So in a picture, this is what the Chaos conjecture is asking. Given any bipartition of a isotropic log-concave density, what is the worst case ratio between the surface area of the bipartition and the volume of the smallest side? So the contributions of this work are that we improve the understanding of log-concave geometry and give faster algorithms in this well-conditioned log-concave sampling setting. Specifically on the geometry side, we show that the norm of the gradient of f of a point x drawn from a log-smooth density that is also log-concave concentrates very tightly around its mean. And by using this geometric fact, we improved the mixing time of the popular Hamiltonian Monte Carlo algorithm to roughly kappa d polylog 1 over epsilon gradient queries to find a mixing time of roughly epsilon. And what's particularly notable about this mixing time bound is that it's the first linear dependence on kappa in the high accuracy polylog regime. It improves upon the only previous linear dependence on kappa by a factor of roughly d over epsilon to the 4. Now, on the hardness side, we also showed a hard density for most common approaches in terms of first order high accuracy mixing, including our own, which shows a linear dependence on kappa. And I should point out there's a lot of remaining work to be done here. For instance, our lower bound is algorithm specific and does not show a lower bound in terms of the parameter d. Great. So the specific nice assumption I'm going to make for the rest of the talk is that the Hessian of f is upper and lower bounded by multiples of identity everywhere, governed by these parameters m and l. And what this m buys us is it's the strong convexity parameter, and it implies that the point x drawn from this distribution concentrates well, namely it has sub-Gaussian tails. And the main new ingredient we bring to the table is that this L parameter, which is the Lipschitzness of the gradient of f, implies that the norm of the gradient also concentrates well. And I'm also going to define this scale invariant condition number to be this ratio between L and M, and I'm going to call that kappa. Cool. So this problem is motivated by posterior estimation Bayesian learning. So say you want to estimate some function, the expectation of some function over your data set drawn from a distribution P. This is too hard to estimate in closed form most of the time, so you just sample repeatedly for P. And in many applications, such as when P is a multivariate Gaussian or induced by a logit function, this P is well-conditioned, and then we can apply these well-conditioned samplers. So I'll remind you that the goal is to produce a point with an epsilon total variation distance of some density that looks like x of minus f of x. And most algorithms in the high accuracy regime follow what's known as the Metropolized Hastings framework, as does ours. And here you want to take a step from your current point that approximately preserves the stationary distribution, which is this target. And then you apply a filtering correction step to exactly obtain this target distribution. And I won't talk too much about the second step because it's standard. But the goal of the first step is to make sure that this filtering does not filter too often. So how exactly do you design this first step? Well, in the general setting, because there's not much structure on its underlying function, most algorithms studied are very simple, such as the ball walk. But in the well-conditioned setting, you can exploit this additional structure about your function f via a first-order oracle. And typically, these algorithms look like discretizations of continuous processes, which attain the correct stationary distribution. And these continuous processes are typically stochastic differential equations. And then here the goal is that you want to discretize this continuous process and argue that this discretization error does not change the stationary distribution too much. So one commonly studied SDE is the Langevin dynamics, where you take your current point and you perturb it a little bit by the current gradient, and you add a little bit of Brownian motion. And I should point out that this is a continuous time process. It's easy to see that this converges to x of minus f of x using well-known techniques. And here's a picture of this. In continuous time, you're at your current point. You displace it a little bit in the direction of the gradient, and then you disperse a little bit according to Brownian motion noise. So what do these well-conditioning properties buy us in discrete time? Well, first of all, even in continuous time, all it takes to converge rapidly is strong convexity. But we as algorithm designers need to discretize. And a typical strategy is you just take your current point and you move it by a little bit of the current gradient for some finite time, and then you add a little bit of noise. And what smoothness buys you is that the gradient is stable, and this helps the discretization process. So the particular discretization strategy that we study is what's known as Hamiltonian Monte Carlo. And this is inspired by the Hamiltonian classical mechanics. Specifically, define the Hamiltonian h of xv to be the sum of a potential energy, f of x, and a kinetic energy, half of norm of v squared. So here x symbolizes your position, and v symbolizes your velocity. So note that if I move these variables x and v according to the other side, namely x moves according to v, and v moves according to minus the gradient of f, in continuous time, this Hamiltonian h is preserved exactly, and this helps us argue about the stability of this process quite a bit. And the key idea here is that if we can expand the space to a more stable procedure, and sample exactly from x with minus h, the x marginal is actually preserved. So by outputting the point x, we get a sample from x with minus f of x. Now let's see where gradient concentration comes into play. So how do you actually bound the mixing time of this algorithm? So we, as other metropolized algorithm analyses, follow the conductance framework. And the basic idea behind this framework is it says that for most partitions, you frequently cross the partition. So consider some partition of the distribution. The main idea is in two parts. You want to argue that this is not a bottleneck partition. So first, you want to show that for most of the points from this density, they lie close to the partition. And second, you want to say that for most of the points lying close to the partition, they cross very frequently. And the idea here is that this means that your random wall cannot get stuck anywhere. And how would you prove such a thing? So recall again that the intuition is that you don't want to cross into these far off regions too frequently, because that's where it's likely to get stuck. And the point is that in our procedure, x moves according to v, and v moves according to the gradient of f of x. Now we get stability of v for free in our algorithm, because v is resampled every iteration. However, you also want to show that for most x, the gradient of f of x is relatively stable. And this is where gradient concentration comes into play. So let's see what was known. In prior work, the fact that x with minus f of x is sub-Gaussian was used to show that the gradient concentrates. So specifically, because x concentrates around the minimizer, and f is a Lipschitz gradient, you can immediately show that these two bounds combine to show that the norm of the gradient is with high probability bounded by roughly square root L kappa d. However, previous work also showed an improved mean bound. Specifically, it showed that the expectation of the norm of the gradient was bounded by something that's roughly a square root kappa times better. And a simple application of Markov shows that with constant probability, the norm of the gradient cannot be too much larger than this, but there remains a gap between these high probability cases and the expectation bound. And our work basically improves the previous statement to high probability, closing this gap. The proof technique we use is that the prior work, in order to show this high probability bound, uses a Poincare inequality with strong convexity to show that the point x concentrates, and then applies smoothness. Now we use a Hessian-weighted variant of this Poincare inequality to get a slightly tighter bound, and then we boost this to a high probability guarantee using what's known as Herbst's argument. So the main idea here is that we're going to bypass this argument of concentration of x and directly argue about concentration of grad f. And I won't get into too many details here, but the main idea is that we're replacing this naive strong Logconcavity bound with a tighter, locally reweighted variant based on the Hessian of the current point. And here is the concentration bound we get. You can see that with high probability, the norm of the gradient is not too much larger than this square root LD factor, which is its expectation. So it turns out that this high probability set brings some subtle difficulties in terms of the analysis. And I won't go into too much detail here, but I will survey it briefly. So the specific issue is that continuous space Markov Monte Carlo chains, which ours is an example of, must restrict to a high probability region because it is unbounded in general. And our conditioning set that we restrict to happens to be non-convex in general. Now, the blocking conductance framework tolerates a little bit of error in this non-convexity. And the issue here is basically that the restriction of a Logconcave distribution to a non-convex set may no longer be Logconcave. But because our set has such high measure, we're able to tolerate this small additive error. This blocking conductance framework also has its own difficulties that we need to deal with. And one issue is that because it's an averaging framework, it's a little bit more difficult to get a high accuracy dependence on the desired accuracy epsilon. And we introduced a new boosting technique, which is able to exponentially boost this warmness parameter by a coupling argument. And I'll sketch it briefly here. So the main idea is that while the total variation distance of your chain is still at least epsilon, namely that the chain is not mixed, the warmness cannot be too much larger. So here beta is the initial warmness. And therefore, I can use this constant accuracy coupling procedure to reduce the measure of the uncoupled set geometrically. And this will give it exponential convergence. Great, thanks so much for coming to my talk. And feel free to reach out if you have any questions. And here is a QR code to our paper.